This is the last lecture, and so what I want to talk about today is how to do some computations of these cohomology groups which control whether or not you can quantize your field theory. So in the physics terminology, the way we're going to do the computations is called descent, and in the math terminology, we're using spectral sequences. So we have some field theory on a manifold M. Fields are I use this notation for local functionals. And these are the integrals of Lagrangian densities. And this is a differential which is the anti-bracket with the classical action. So we often break this up into two terms. This is from the quadratic term. And what we saw last time is that H1, this is the set of possible obstructions to quantizing. H0, these are the possible counter terms you can add on. So possible deformations of my theory. And actually this keeps going. H minus 1. These are symmetries. And it keeps on going like that. In fact, as part of our the general descent argument, we're going to see how, these guys are densities you integrate over the top dimensional space. But we'll see that you can relate them to densities you can integrate over smaller dimensional spaces, where when you shift the cohomological degree. So these guys, local functionals of degree minus 1, every one of those will give you a current of degree 0 that you can integrate over a codimension 1 manifold. And similarly, things in degree minus 2 will give you something you integrate over codimension 2 manifolds. Okay, so there's a generalization of this when we want if we're working on flat space and you ask that your theory be normalizable, so that has reasonable UV behavior, this story can be generalized. But maybe we'll discuss that later. So how do we compute this? So let me give you the general method and then work out some examples. If I take a point in my manifold, we let, I never know good terminology for this, but A sub x be the cochain complex of local operators. So this is, of course, functions of fields and derivatives. And since we're in the BV formalism, also ghosts and so on. With then the differential so we wrote down some examples of these spaces and how they can be formed. And we'll do another example in a little bit. So what we're going to use is that this cochain complex, well, as I vary x, it's going to form an infinite dimensional vector bundle, a graded vector bundle. But more importantly, so a section of this bundle will be a local will be something which assigns to a point a local operator at that point. But a really important feature of this bundle is that we can differentiate sections. So locally, if O is a local operator, at some point, say 0 in Rn, we know how to differentiate. Makes sense. This is something you can do to local operators. So suppose I had let's just work in a local situation where the bundle is trivial. And then if I had a family of local operators, depending on a point in Rn, so if I have then I can differentiate this with respect to any variable just by the Leibniz rule. I don't want to go into this too much, but so for the mathematicians in the audience, the way to understand this is this space A, it's a commutative algebra, and it's functions on jets of fields. So it's the algebra of functions on jets of solutions to the equations of motion modulo gauge. Now, anytime we do anything with jets, we have a natural connection. So this is a dx commutative algebra. It is the algebra. So for the founds of D modules, you could say we know that a D module is something we get when we have a linear differential equation. When we have a nonlinear differential equation, we'll get a D space because it's nonlinear, whose functions will be a D algebra. Since the solutions to the equations of motion of our theory are nonlinear PDE, they'll be described by some D algebra, and this is what this is. So maybe let me write down one example just so we are not completely lost. to the example of the free scalar field, phi, and this has its antifield, phi star. So A is going to be given by functions of phi, phi star, and derivatives. So the linear functions well, what's a linear function? I can just take an arbitrary derivative differential operator applied to phi and evaluate it at a point. So the linear functions consist of differential operators on my manifold in degree 0. This is the functions of phi, and differential operators on my manifold again in degree -1. This is the function of the antifield. And then I want to mod out by those guys which vanish on solutions to equations of motion. So I get a cochain complex where the differential is given by the right multiplication by the Laplacian. So at every fiber, I'm just taking polynomials in the dx's, and with the differential given by the Laplacian. But I'm making those into a bundle, so I'm allowed to take differential operators whose coefficients are functions of the manifold. Make sense? Okay, and then so all functions, all of A, is then the symmetric algebra of this guy. So like fiber-wise, I can take polynomials. I can differentiate phi a bunch of times and take a product of a bunch of those. That's why I pick up a symmetric algebra. Making sense to you guys? Okay.
Sorry, did you say you multiply the Laplacian on the right?
Yes.
That is.
Okay, let me extend. So a functional linear in the fields might be something like f of x times some differential operator. And here, this is in degree 0, e of x times some differential operator. And the differential I call q is going to be some d of x dx del xi squared. So I'll pass it over here. So that like at each fiber, if I fix x at each fiber, I'm just hitting it with the Laplacian, and I'm not differentiating the coefficients. So the math thing to say is that because we're multiplying on the right, it commutes with the left action. So this is a complex of left demodules. And I've been using the word demodule. I don't know why people invented this term. A demodule is just a fancy way of saying a vector bundle with a flat connection, an infinite dimensional vector bundle with a flat. That's all it is. So why are we introducing this? So it turns out that there's a nice way to. So Lagrangian densities are, of course, related to local functions, so to local operators. Lagrangian densities are just top forms on M with coefficients in this bundle. But we really care about Lagrangian densities up to total derivative because we're integrating them. So the local functionals, the thing which control the deformations, modulo p of now, if you look at this, you might immediately think that you might want to extend this to the RAM complex with coefficients and local operators. So the nice thing, which we're going to use to be able to compute stuff, and which underlies descent arguments, is the following. So if we consider the double complex, whose columns are given by forms with coefficients and local operators, and on each column I have a BRST operator, because local operators have their BRST operator, and the horizontal differential is a de Rham differential. So this double complex has a kind of long and rich history. It's basically, because we're studying an PDE given variational PDE given by the variation of a Lagrangian, what we're studying is really the calculus of variations. So this double complex is basically the same as the variational bicomplex people study in the calculus of variations. At least in the case when there's no gauge symmetry. So the nice thing about this double complex is that it's exact along here. So that the cohomology, the horizontal lemma, the horizontal cohomology lives in the top degree. So, and therefore it's omega n. The top form is modulo the input b. Yeah?
It sort of would have thought like the variational bicomplex, the columns would look more like kind of forms on the A space, like there would be things, of the form like delta of yield or whatever showing up.
Did I get it wrong? Maybe I got it wrong. Okay. Thank you for the correction. Maybe there's more than one bicomplex that you can write down when using the calculus of variations. Okay, so what's nice about this is that it allows us to say that the cohomology of this piece is the same as the cohomology of this whole double complex, total cohomology of the double complex. And then we can compute that in a different way. corollary the complex describing obstructions, deformations of our theory has the same cohomology as forms in the manifold with coefficients in A as like the total cohomology of this complex. So I think what I call Q up there, I'm calling, I don't know. Here's the differential on A. Maybe I'll just call it D sub A. The differential on local functionals, the de Rham differential. And this shift means n forms are in degree 0. Okay, so and then there's one more step, which is what like the descent method has one more step, which is that we can compute this by a spectral sequence. Going from hi of m manifold with coefficients in hj of a hi plus j of the total complex. So let's do some examples so we get a feeling for why this is useful, unless there's any questions.
The lemma, does that have something to do with like this sort of type of ADE or modeling with
Well, it's because we're doing things in this kind of derived way. So everything is going to look like the symmetric algebra or tensor exterior algebra B. Copies like that. So A will be free as a D module. With some differential.
So what are we aiming at?
Pardon?
Just to give a bit of perspective, what are we aiming at with the free theories?
So we're aiming at, so we have this complex, this H1 describes the anomalies. Now, the definition of this complex is a bit tricky. A priori, it's tricky to compute it. So what we're doing is we're rewriting it in terms of in these terms, which will be easier to compute. Because we do know, we know how to compute the cohomology of local functionals, but when we compute the complex given by Lagrangians, the difficulty in the computations involves that everything is taken up to total derivatives. So it's hard to write a good basis for.
I'm just asking more like, I get where anomalies arise if you have a gauge theory, but for the free field theory, what is...
All right, so for free field theory, this is... I agree the free field theory is a bit of an artificial example.
Just to...
You may care about its symmetries. The other degrees of this complex tell you about its symmetries, for instance.
So like adding operators proportional to the equations of motion, something like that.
Yes.
I see.
Uh, yeah, but and you also care about, H0 because you might care what possible counterterms can I add on that's controlled by H0 of this complex. And again, that might be, if you have some complicated field theory, it might be difficult to figure out what are the gauge invariant things I can write down modulo those which can be absorbed into a field redefinition. And this computes that for you.
Is that double complex also for the sigma?
Possibly.
You write the form between OX and
Yes, that is absolutely that. Or you can also think of it as omega x tensored derived tensor product over D with A. Yeah. Yeah. Okay. So I'll start with an example which is maybe not the first example you might think about when you're studying gauge theory. But I want to do it because it's kind of interesting and it's also much easier than the onions theory. So if I take sigma topological surface on sigma cross C, I'm going to all the details. It's a theory. We have a theory on sigma cross C. The field is A. It's a one form with no Z component. And the Lagrangian is integral dz times the translamus action. Z is a coordinate on this space here. So what are local operators? Well, the fields so the solutions to the equations of motion say that the curvature in the sigma directions, we call them x and y, so what this means is for each point here, I have a flat bundle here, and for each point in sigma, I have a holomorphic bundle on this plane, and they're compatible. The parallel transport preserves the holomorphic structure. So the key point that all solutions locally are trivial. And locally, they have symmetries. Well, the symmetries are those of a flat bundle on sigma, which is just constant, and holomorphic bundle here, which is a holomorphic gauge transformation.
So this is not this, but is this theory covariant in the usual sense?
It doesn't have Lorentz invariance. And maybe I shouldn't have chosen this example. So the symmetries are given by those gauge transformations, which can be holomorphic functions on this plane. So the algebra of operators, because the equations of motion, every solution is trivial, we can't build any operators of ghost number 0. All the operators are built from the ghosts. They're built from the ghost and all of its derivatives in one direction. So how do we... So we might look at this and we see that we have a very... Even though... I mean, this theory is pretty simple. Even so, we have this very large algebra of local operators whose cohomology we would like to compute. So there's the math way to write this guy, this space of local operators. They're the Lie algebra cochains of this infinite dimensional Lie algebra of currents with values in G. Now, at this point, we might think this is infinite dimensional Lie algebra, and the cohomology of infinite dimensional Lie algebras can be very difficult to compute. But fortunately, this particular example, the cohomology was computed. And if I recall correctly, the only cohomology is that given by the ghosts without any derivatives. So, could be that I'm misremembering, but certainly this is the only relevant cohomology that will be made of reference. Okay, so this is great because this complex is it's a very standard thing to compute this complex. Of course, yeah.
In the initial statement, are you using like translation invariance when you say or something like that when you say that those are all local operators? Or?
No, this is literally all the local operators. Because
You can have something like Zi delta C or Z delta.
this is the fiber of the bundle at a point.
Okay, yeah. This
Like the fiber of the D bundle. Yeah, okay. Yeah, but yeah, if we were to take sections, then we would have what we said. So finally, the Lie algebra cohomology of P is isomorphic to the Lie algebra the Ram cohomology of the compact form. This is a standard fact in Lie theory. The point is, I can look at those differential forms which are left invariant. That complex will be exactly the complex that we described. And there's always a projection onto the left invariant forms, and the kernel of that projection is the cohomology. So for example, if G is SL2, then this Lie algebra cohomology G is the cohomology of the three-sphere. Okay, so now let's plug this back into our computation. Say, what are the possible symmetries and obstructions and deformations? Well, there are going to be forms with coefficients in this D module, whose fiber is, say, the cohomology of the three-sphere or the cohomology of the compact group. Now, because this is a finite dimensional, because the fibers are finite dimensional, it follows that the connection is locally trivial, because all finite dimensional flat bundles look the same. And there might be some monodromy globally, but there really can't be. In this case, there's no global monodromy. So, in sum, we find that the obstructions and deformations look like the cohomology of a sigma times C, coefficients in the cohomology of the compact group. But this is, of course, the same thing as the cohomology of sigma times C times G, both with a shift of 4. So to figure out whether or not this theory may have some kind of anomaly, we're going to look at classes of degree 1 here, or equivalently, 5-dimensional cohomology classes on this. So we see anomalies. H5 of sigma cross C cross G. And, well, if sigma is a Riemann surface, there are elements there. So there's a class in H2 sigma answered H3G, which looks like, say, because this is one-dimensional, and this is also one-dimensional, so there is a potential anomaly. And in fact, in this case, it really exists. I can take the first Chern class of the tangent model of sigma, wedge the marker tan 3 form. This is called a framing anomaly for this theory. Okay. How did people find this computation?
So what happens once you know
say you trivialize the anomaly, then what do you do?
When you have your theory,
Yeah.
you compute things about it. Maybe you would compute things about the space of local operators and their OPEs or the structures. The theory would just kind of topological like this. You can play topological games, study categories.
Where did that terminology come from? Why is it called a framing now?
Right, because the first Chern class vanishes if I can find a nor vanishing section of the tangent model of sigma. And that's a framing. So it's like, because sigma is always it's oriented, right? So if I have one vector, I can take the vector pointing 90 degrees, and I get a framing of the tangent model.
Yes.
So I kind of get a bit obsessed by these cohomology computations. I find them really fun. I don't know.
So if the framing anomaly exists, that means that you can't quantize the theory, or?
You can as long as the first Chern class vanishes. So you could do it on like a frame movement surface. So it's a frame TFT. Let's see. Okay, so what? So I hope this. So what's nice about this method, right, is that it reduces the really complicated cohomology problem you originally had to something just about topology. And then, so the anomalies now have some kind of pretty clear topological meaning. It can be tricky to go backwards and say, given this cohomology class, what is the explicit Lagrangian which represents it? And that procedure of going backwards is what people when people do descent. The reason it's tricky is we've done a bunch of spectral sequences, and we have to. I don't know if you're familiar with these techniques. You kind of have to climb up the spectral sequence to get to the top and find a Lagrangian representing it. So it's possible, and there is an explicit formula, but. So let me say a little bit about.
So then the infinitesimal symmetries of this thing correspond to classes in each form.
Yes.
And then I see that's going to correspond basically to things in each one of my Riemann surface.
Yes.
So symmetries have to do with like monodromies around loops in my surface. Or?
Yes, that's a really good point. Well, I think you're kind of seeing Noether's theorem in action. Because I can integrate them over like 3 cycles.
You can integrate
Like over 1 cycle in the surface, maybe times c if you want.
right.
What about X0 sigma tensor resection files?
Yeah, so that's a good example. So that looks like it might be an anomaly, but so if this also for Yang-Mills theory, this looks like it might be an anomaly. This is equal to or if P is SLN and bigger than 2. Otherwise, it's 0. Draw all of the Lie algebras. Now, what you notice is that this Dinkin diagram has an automorphism. The type A Dinkin diagram is an automorphism by rotation, and that acts non-trivially on this class. Now, the theory was invariant under this automorphism, so therefore the anomaly cannot be there. If I had some matter living in some representation labeled by one of the nodes of the Dinkin diagram, then I couldn't use this argument, and potentially the anomaly would be there. So those are the anomalies that appear in UCD. The chiral anomalies of chiral matter. I think, anyway. Yeah. So we want to ask, the thing we want to know is like, what are local operators? So we'll write down this complex. This computation has some tricky parts to it, if I remember. The local operators, to figure out what the local operators are, we should first take the cohomology of this complex at the level of jets. So if we do this, we find degrees -1, find G, degree 0, 1, 2. Up here we find, it turns out if you compute it, there's nothing up here. It's not totally obvious, but you just have to sit down and do it. But there's some stuff in degree 0 in these two degrees. I'll call this B. And these are certain, like, infinite-dimensional spaces. And they live in the adjoint representation. So local operators so cochains of G, coefficients in symmetric algebra now, these things here, MA dual and B dual, these are certain D modules. And they can be quite complicated D modules. And you don't really know, it's not going to be easy for you to compute the de Rham cohomology with coefficients in these D modules. So we're going to break this up into an easy piece. The easy piece plus this contains all the higher symmetric powers. And this piece is hard. Now, fortunately, you can use scaling arguments to get rid of the hard part. We care about Yang-Mills theory as a normalizable theory with a nice UV description. That means we can't add on counter terms with lots of derivatives. That will mess us up. And also, it also means that anomalies with lots of derivatives don't appear. So scaling arguments say I got plot space anyway, will exclude the hard part. Because you're interested in things of dimension 0, and anything here must involve some functions of the fields, and you can convince yourself you can't be dimension 0.
So, I guess to be able to do this in general, you would require asymptotic freedom. Because, I mean...
The sign of the beta function doesn't matter.
Yeah, no, but one thing is that depending on what the flow does, wouldn't I be worried about...
Yeah. See, so you couldn't apply this to Yang-Mills theory in dimension 5 because the classical flow is kind of the wrong way. You would expect counter terms with lots of derivatives to appear, and anomalies with lots of derivatives. So things would be much more complicated. Also for gravity, things would be much more complicated. So for a renormalizable theory, you can use this kind of argument. And I'm simplifying things a bit. You need a little more than scaling arguments. There's another argument you need as well. So in this particular case, but scaling arguments gets rid of most of it. Okay, so now we're left with So I think we're kind of seeing a pattern, right? That we always have this universal piece, cochains of my symmetry algebra with coefficients in the trivial representation. And that will always contribute some kind of standard class of anomalies. This is what was studied by Semino. And then there's always a difficult part you have to analyze on a case-by-case basis. So here we're left with standard anomalies, which on, say, a 4-manifold are in, again, the cohomology of the manifold times the compact group is shift 4. Just for the same reason we saw earlier. So let me just so if M is O4, the anomaly is then in H5G. And again, for pure gauge theory, can be excluded by the Lincoln diagram symmetry. So being a bit sloppy here, we exclude the hard part. Mostly, we find only one deformation. So if you compute the hard part, most of it is thrown away by scaling. And there's only one thing left, which is in the degree to give you a deformation, and it is the Yang-Mills coupling constant. So we find there's one deformation, and in type A, there's one anomaly which can't arise when there's no matter. No, it wasn't very. Any questions?
Could you give like a schematic explanation of like these kind of typical descent calculations people do?
Right.
How those would be related to anomalies?
Yeah, so the way it goes is, say in this case, there's an anomaly coming from H5 and a symmetry coming from H3. Well, we did this by this kind of abstract computation, so we didn't write down any Lagrangian of degree 1, which gives you this anomaly. And we should calculate what that Lagrangian is by undoing the spectral sequence. So what you need to do so in this case, so like descent for the anomaly, we have a class in omega 0 of OR4 with coefficients and local operators of degree 5 given by trace C5. So it's BRST closed. So it's an A. But it's not closed in this double complex. So the abstract arguments tell us we can add corrections to make it closed in the double complex, and our challenge is to find formulas for those corrections. So we need to find, say, alpha 1, which is a 1 form, in O4 with coefficients in A4. So that the differential local operators applied to alpha 1 plus the de Rham operator on alpha 0 is 0, or we take alpha 0 to be base equal to 5. So how do we do this? The de Rham operator alpha 0 is sum 5 dx I trace del x I c to the fourth so you want to write this as the BRST operator of something, and you can kind of guess, you know, the derivative of the gauge field is given by the gauge variation of the xi component. So the derivative of the ghost, or the variation of the xi component of the gauge field. So you guess that alpha 1 should look like of the form where we take the I component of the gauge field. But maybe this is not exactly, off the top of my head, I can't see if this is exactly what you want, because maybe we need another term. I'm not quite sure. And then you just continue. You say you want the de Rham alpha 1 plus A alpha 2 is equal to 0, and so on. Now, when you get to the top, that is your Lagrangian, which represents the anomaly. So alpha 4 is a 4 form in R4, with coefficients in local operators of degree 1, and this is the anomaly. The Lagrangian represents the anomaly. Like, if you were to write down some Feynman diagram to see if you had an anomaly or not, the thing you would be computing would be this piece. And the arguments we've been giving tells you that this piece here contains all the data, and this piece here also contains all the data. It's just that this piece is easier to see.
So like concretely, you would really expect that exact thing to show up in some like diagram or something.
Yeah. Absolutely, yeah. And if I personally was to do this, you would see that this is kind of a tedious procedure. So I would use some trick to say that, like, I could compute the cohomology, it's one-dimensional, I will guess a representative. Any questions? Yeah.
This is the same procedure that people call descent, that like back to like Witten's paper on topological signal models.
Yes, although it's older because I think we're writing in the 70s maybe. But yeah, and as you can see, it is just a spectral sequence. Yeah, I sometimes feel a bit unsatisfied with the physics treatment of this because I think anomalies can be a lot more complicated than you sometimes see. I mean, people sometimes assume that these kind of easy anomalies are the only ones there, but that's not true. It can be more difficult than that, especially for non-renormalizable theories. I think on curved manifolds, I don't think if you were to study Yang-Mills theory on 5 dimensions on a curved manifold, I don't know if the literature will tell you or not satisfied if there's an anomaly.
Is the situation similar for supersymmetric movements?
No, there it's much better because there you should be looking at like the homotopy invariance with respect to the supersymmetry algebra. And that really cuts down even the bad part. I mean, I'm not sure how well documented it is, but I'm happy to believe that there's a proof somewhere.
So, could you phrase what we usually call the non-renormalization theorems? I mean, is there an easy way to see what they are in this language?
So what do you mean that the what are those theorems?
Like that there are certain quantities that don't get corrected.
Oh, in supersymmetric case.
Yeah.
Oh. I think the slickest way of phrasing those would be to say that those are quantities that can be detected by some twisted theory, and then in the twisted theory it tends to be easy to see that there can't be a beta function. That there might be an argument along these lines, but I don't know.
Also, there's statements about like one loop exactness of anomalies and so on.
In the supersymmetric case, or in general?
So like when people compute the anomalies in the static model, it's
Yeah.
always just this one loop diagram, and then you say, well, I see that it cancels, that's it.
Yeah, well, I don't. Maybe there's something special. There is like some guy. There is like an argument that somebody made that's saying anomalies are always at one loop.
Right.
But I think that is clearly wrong, because you can, when you introduce a one-loop counter term, can clearly introduce a two-loop anomaly. Like I don't. So I don't. So but maybe I don't want to cast doubt on like specific cases that people have studied with the standard model because I don't know the details. Maybe there's something special happening there. I mean, in cases where everything is very normalizable, and the anomaly there might be only one anomaly, which takes the same form at each order in the loop expansion. And so maybe the higher loop arguments will cancel for similar reasons.
What about something like the chiral anomaly in 2 dimensions?
Chiral gauge theory?
Yeah, like just one plus one that
Well, typically those theories are themselves one loop exact.
Right.
But actually, no, there are interesting. There's a really nice paper of C. Lee where he studies an anomaly in a sigma model. So you know that you may not be familiar with anomalies in a beta gamma system. Right? The curved beta gamma system is an anomaly proportional to P1 of the target. But there's a sigma model called symplectic bosons, where if I take, say, sigma model from sigma x, where this is holomorphic symplectic, so he computes all of the anomalies, and he finds there's a, at one loop, there's the usual one, it's P1 of the target, but he finds that there's corrections to all orders in the loop expansion. All given by diagrams of two vertices. And they're related to certain invariants of holomorphic symplectic dynamics. Related to Wronski-Witten invariants. So I think there are definitely examples where anomalies exist in all orders.
Would it be significantly harder to use this method to compute gravitational anomalies? The anomalies that arise if I couple the Q to some curved background, maybe with certain amounts of surface.
I mean, the general spectral sequence method applies in a curved background.
Well, what I mean is, for example, the Donaldson-Witten twist has an interpretation in terms of a particular n equals to supergravity background,
Yes,
where some fields are turned on.
that's right. The principal bundle for the Orr symmetry.
Yes. Now, not with so much formality, but one can try to write down other terms using the supergravity background fields that are turned on in the Donaldson-Witten twist and find what would be the potential anomalies of the partition function of Donaldson-Witten theory. And the anomalies turn out to be some topological invariants of the background.
So this, maybe you mean anomaly in a different sense, right? Because if I fix my supergravity background, the Donaldson-Witten theory itself is defined. The theory has no anomaly. It could be, however, that the partition function, as a function of the supergravity background, is a section of some non-trivial line bundle. Yes.
What about a simple case like the wild anomaly? So 2 dimensions.
Yes.
Or if 2 dimensions, like usually there's a story which involves saying we write down candidate and anomaly terms. So we just by power counting, write down functions of curvature, derivatives, and so on.
Yes. I think that might be related by these kind of descent arguments with these cohomology calculations.
So it's,
And then you look at a diagram to see if it actually appears.
yeah.
Yeah. I think I would do the same thing. Yeah, if I was studying, I don't know, theory, some curved beta gamma system on a Riemann surface, I would find on a curved Riemann surface, I would find that there's an anomaly associated to that diagram, which is like C1 of the target and C1 of the source. In fact, it's very similar to the one we were discussing for Dietrich-Simon's theory, where when the 4 manifold was curved, there was a kind of C1 of the 4 manifold.
Is there a relationship between anomalies and like the potential failure of the quantum master operation trouble?
Yeah, that's what an anomaly is the failure of the quantum master operation network. So these cohomology groups we're computing are like the obstruction, where the obstruction to solve the Q meet will live.
Oh, like order by order.
Yeah.
Yeah.
So you want to figure
I was here last week, yes.
You talked about that just last time. I actually did watch some of the lectures, but I didn't watch last class.